Let's talk about capacitors very, very briefly. Capacitors are very useful for correcting power factor when you have a poor power factor because of large inductive loads that help to bring your power factor closer to 1. Let's talk about how they work, and then let's talk about why capacitance it increases in parallel circuits and it decreases in series circuits. So it's the reverse of what's happening with resistors. With resistors before, we saw that they decreased in parallel, and then we saw that they increased in series. Okay, let's start with how capacitors work. So this is a typical capacitor that you see on screen. You've got two conductive plates. You've got a dielectric material between them. It can be air, it can be glass, it can be a variety of different materials. Because this is a recap of DC theory, I will go through capacitors for DC theory in a future video. I'm only going to go through what we need to know for AC theory. So you've got your conductive plates and you've got a dielectric material. If you introduce a potential difference, a voltage, what's going to happen is that you're going to have a charge build up on one of the conductive plates, right? You're going to have electrons want to go to the other side. And different things happen as you either increase the value of D here, the distance between these conductive plates, or you increase A, the surface area of these conductive plates. So the parallel and the series circuits with capacitors impact these two variables. Okay, as promised, guys, we're going to go through how or why capacitance decreases in a series circuit and why it increases in a parallel circuit. So let's start with parallel circuits here. So on screen you can see that there's three capacitors in parallel: 300 microfarads, 200 microfarads, 470 microfarads. You got a 50-volt supply. And what we are saying is that the capacitance will actually increase here. That's what this equation here is saying. So why is that? When they're in parallel, like here, what you have to think of is that you're not increasing the distance between the conductive plates. All you're doing is kind of stacking them on top of one another like this. So I won't draw the full circuit, but I'll just draw 3 capacitors. Right? So those are C3, C2, C1, 3 capacitors. Okay? What you can think of is that this forms an equivalent capacitor that looks something like this. That's the equivalent capacitor. So notice how the distance hasn't changed. So this is the distance D. Hasn't changed. But the compared to when there were 3 individual capacitors. But what you have definitely increased is the effective area of the conductive plates. Notice how each one of these had the surface area for the conductive plates equal, and it was quite small. But look how much bigger it is here. So the area has absolutely tripled. Okay. So you've tripled, roughly, we're just saying. Okay, we've tripled the surface area, but we've kept the distance between the conductive plates the same. Then it makes sense that the capacitance would increase as well. So let's actually show it using this example here. So the capacitance total here would be C1, which is 200 microfarads here. I've mislabeled the slides, the figures. 200 microfarads capacitor 1, 300 microfarads capacitor 2. And capacitor 3 has 470. Okay. So now, let's bring up the calculator. We've got 200. We've got 300. We've got 470. And what does that give us? It gives us 970 microfarads of total capacitance. Okay, that's the total capacitance of this here. Okay, so then for the next part of understanding capacitors in parallel, let's just work out what the total charge would be for this equivalent capacitor and what each individual charge would be as well in coulombs. So let's start us off. Let's start by working out what the total charge would be. So Q total would be capacitance total multiplied by voltage supply using this equation here. What that tells us is that you're going to have 970 microfarads. And importantly, we have to convert this back into farads. So multiply by 10 to the negative 6. Okay, that'll turn it back into farads. And then we have to multiply it by the supply voltage, which is 50 volts in this case. Let's bring up the calculator. The calculator will tell us that 970 multiplied by 10 to the negative 6, which will turn it back into farads again, multiplied by 50 volts will give us 0.0485 coulombs of charge. 0.0485. We'll do it to 2 decimal places, to 3 decimal places. 0.049. 0.049 coulombs of charge. Okay, let's do it for capacitor 1, 2, and 3. So what about Q capacitor 1? That's going to be the capacitance of capacitor 1 multiplied by supply voltage. That gives us 200 microfarads multiplied by 10 to the negative 6 times 50 volts. And the same would occur with capacitor 2. It's going to be capacitor 2, 300 microfarads. We're going to change that back into farads. 50 volt supply. And the same with capacitor 3, which is a 470 microfarad capacitor. And again, 50 volts. Let's put all of those into the calculator and record what the values, and they should equal, when we add them all together, 0.049. So let's grab our calculator. The first one we got to do is 300 by 10 to the negative 6 multiplied by 50 volts, 0.015. Coulombs. Let's do the next one. 300 microfarad capacitor. Change it into farads. Multiply it by a 50 volt supply. It's going to have a charge of 0.015. Coulombs. Did I just do that twice? Oh, my bad. Hold on. I did that twice. The first one was meant to be 200 microfarads. let's make a quick adjustment there. So let's do the 200 microfarads. This guy here should be 0.01. My bad. So we'll just change this into a 0. This is still correct. And then the final one, 470. We're going to have 0.024. Just 2 decimal places. Charge. That's a coulomb. So if we add those three values together, just to confirm it, that we aren't going crazy, 0.024 plus 0.015 plus 0.010, 0.049 coulombs. Okay, let's discuss how our capacitance actually decreased in series. Okay, the last one I'm going to discuss is what happens, or just to clarify what happens when capacitors are added in series and why the overall capacitance decreases. It's one thing to talk it out, it's another thing to actually show it. So, before, we're talking about capacitors and how when they were in parallel, what happened was you effectively increased the area, the surface area of the capacitors, right? It ended up something like this. Like you ended up having for the same distance, you had a much greater surface area compared to each individual capacitor having a smaller area, right? So 3 capacitors in parallel gave that before, right? Okay, so what happens in series then? I tried to talk it through, but it's better to show it. What's going to happen is these 3 capacitors right, so you got C1, 1, 2, 3. Okay, let's switch color just to show what happens when they're added in series. Remember that capacitors only use 2 conductive plates. When you add them in series, what's going to happen is the furthest conductive plates, these ones here, are going to be the ones that actually form the conductive paths. So think about it like this. So all of this space here that was previously another conductor, okay, is now just, you can think of it as like the dielectric material, right? That's the conductive plate number 1, conductive plate. That's one side of it, and that's the other. That's the other conductive plate. So with that being said, what's happened is you've increased the distance quite a lot, d, but look at the area. The surface area, the area of the conductive plates, these guys here, has not changed from here. It's the same A, but you've increased the distance. So what does that mean? It means that in order for charge to build up on one side of the capacitor, right, compared to the other side, electrons need to transverse or cover a much greater distance. And that there is why you have a decrease in capacitance. The electrons have a greater distance to travel. So let's actually show what that does with the calculation. So in this case, it says the capacitance total is going to be 1 over each capacitor, taking the inverse of that. So what would it be for this question? Well, capacitance total would be 1 over 470 microfarads. Ooh, I should move this lower. Just because, let's move it lower. CT is going to be 1 over 470 microfarads plus 1 over 300 microfarads plus 1 over 200 microfarads. Okay? Take the inverse of that. That'll tell us what the total capacitance is. We're going to have, let's open up these brackets. Add the fraction in. 1 over 470 plus 1 over 300 plus 1 over 200. Inverse of all that. Total capacitance comes out to be 95.59 to 2 decimal places. Microfarads. So what you can see is that the total capacitance in series is smaller than the than the capacitance of the smallest capacitor. It has to do with this. It's just a much greater distance that has been generated, an effective distance for electrons to travel in order to form the charge across the conductive plates. Okay, so then let's, with this being in series, okay, the total current flowing through, give me a second. So, we know that this is in series, okay? The total current flowing through the circuit is going to be the same at this point here and at that point. So the same current value goes through each capacitor, okay? The reason that's important is because the total charge across each of these capacitors is actually going to be the same. So the total charge will be equal to the charge from capacitor 1, which actually be equal to the charge over capacitor 2, same as capacitor 3. And that's because they're all getting the same amount of current. The only thing that's going to change is the voltage drop over each capacitor. So with that being said, let's find the voltage drop using the equation C equals Q, C equals Q over V. Remember, if it's a series circuit involving capacitors, the charge is the same over the entire circuit because the current is the same going through each capacitor. And just as an aside, we'll do this in DC theory. The reason why that's the case is because the way you find charge is you take the current and multiply it by the time. And if each capacitor is getting introduced to the same current, I, for the same amount of time, they're all going to have the same charge. Just as a note. Let's rearrange this to find the voltage drop. The voltage drop over each capacitor would be Q divided by C. Okay? So let's find the voltage drop over capacitor 1, the voltage drop over capacitor 2, and the voltage drop over capacitor 3, and this will end our revision of DC theory. So in order for us to find Q, we've got to find what's going on here. We've got to find the total. Need somewhere to write it. Let's do it up here. Q T would be the total capacitance multiplied by the supply voltage. Okay, so the way we find the total charge is by saying the total capacitance, which we found to be 95.59, multiplied by 10 to the negative 6, and we are going to multiply that by the total voltage, which is 50 volts. Let's go to the calculator. And what we are going to see is 95.59 multiplied by, brackets first, multiplied by 10 to the negative 6 multiplied by 50 volts. The total charge is 0.0048 coulombs. Just double check that. Yep. Okay, so let's find the voltage drop over each capacitor. So V equals the total charge, which is going to be 0.0048 coulombs. We're going to divide that by the total capacitance of capacitor 1 in farads. Capacitor 1 is 200 microfarads, so it's going to be 200 microfarads by 10 to the negative 6. Let's do these. Let's do all of these first. So then we're going to capacitor 2. We're going to have the same charge, 0.0048 coulombs, divided by 300 microfarads by 10 to the negative 6. Capacitor 3, likewise, is going to have the same charge, 0.0048 coulombs, running out of space, over 470 by 10 to the negative 6. Yikes. Let me fix that up a little bit. (10 to the negative 6). Okay, let's put all these in the calculator and let's see what we get. So we've got 0.0048 over 200 by 10 to the negative 6. 24 volts over the first. What about the second? We've got 0.0048 over 300 by 10 to the negative 6. 16 volts. And the final one we have 0.0048 coulombs being divided by a 470 microfarad capacitor, but we have to change it to farads, 10 to the negative 6. That gives us the remaining 10.221. Now if we add all these values together, we get slightly more than 50. We get at 50.21 volts. I'm just going to write here, VT 50.21, which is very close to our actual supply, which was rounded to just given as 50 volts.